Okay, in today's lecture, we're going to cover the section 11.2 material on one-sided limits and limits involving infinity. And the one-sided limits we had started to talk about intuitively at the end of the section 11.1 material. So we'll talk about those in much greater detail here. So let us, as an example of one-sided limits, consider a problem that we had finished the previous section with, namely to consider a function f, which is a piecewise function defined as follows. So f of x is equal to -1 if x is negative, and +1 if x is greater than or equal to 0. So for this function, we are asked to sketch the graph of y equals f of x and find the limit of that function as x approaches 0 if it exists. So we had looked at this problem at the end of the last section, so let's review what we had seen there. So in the xy plane, we want to sketch the graph of our function. And f of x is defined to be a constant, -1, for all values of x that are less than 0. So for all negative values of x, we have a constant y value of -1. And when x is equal to 0, the value of our function changes from -1 to +1. So when x is equal to 0, we jump to a y value of +1. So we're going to have a closed point at 0, 1. And for all positive values of x, our function remains at that constant y value of 1. Now, for the part of our function where x is less than 0, as we're approaching 0 here, we're going to have an open point at 0, -1, because this inequality was a strict inequality. When x is equal to 0, we're not equal to -1, but it jumps to +1. So we're asked to find the limiting value of this function f of x if it exists. And the way that we had considered this in the last section was to consider a table of values for x and the corresponding f of x. So here, if we're considering approaching 0, well, at x equals 0, our function f of x is defined as 1. Now let's say that we're taking values of x which are close to 0 but not equal to 0. So remember, that's the idea behind a limit. So maybe if I take a value a little bit bigger than 0, let's say 0.1 or 1/10, well, since this value of x is positive, we know f of x is defined as 1, since f of x is 1 for all positive values of x. Now, if we move a little closer to 0, let's say we take 0.01, well, this value of x is still positive, so our y value, or f of x, is still 1. Now, if we take values of 0 that are our values of x that are close to 0, but a little bit less than 0, say, for instance, -0.1, well, anywhere that x is negative, the value of our function, f of x, is defined as -1. So if I move a little bit closer to 0, let's take -0.01. Since this value of x is negative, we have a value of -1. So the question is, well, what is happening with the values of our function as we get close to 0 but not equal to 0? And we can see from our table that as we're closing in on 0, from the left-hand side, that is, if we're taking values of x which are less than 0, but moving towards 0, the values of our function are always -1. So our limiting value appears to be -1. However, if we're taking values of x which are approaching 0, but to the right-hand side of 0, that is greater than 0, and we start to close in on 0 from that right-hand side, the y values for our function are always equal to +1. So it seems like if we're approaching 0 from that right-hand side, our limit should be 1. So as we mentioned at the end of the last section, well, there's no single number that our function f of x seems to be approaching as we're closing in on 0. So we would say that the limit does not exist in this case. Now for this type of problem, we can define what are called one-sided limits for our function. So here we would say that the left-hand limit of f of x as x approaches 0 is equal to -1. So we saw if we're taking values of x that are closing in on 0 from the left-hand side, the values of our function are closing in on -1. So this is defined as a left-hand limit of our function as x is approaching 0. And the notation that we use for a left-hand limit is similar to what we would use for a limit. So we have LIM for limit, and in the subscript we have x is approaching 0, and notice there's a little minus sign beside the 0. So that minus sign means that we're considering a left-hand limit. So we're taking values of x that are a little bit less than 0, or to the left of 0. And the function f of x that we were considering is denoted here as f of x, and our limiting values seem to be approaching -1 from that left-hand side. Now similarly, we can define a right-hand limit of our function f of x as x approaches 0 as being +1. And denote it in a similar fashion. We would say the limit as x approaches 0 from the right-hand side. So notice we have a little plus beside the number 0, which is used to denote a right-hand limit, and it means we're considering values of x that are a little bit greater than 0 or just to the right of 0. And as we were approaching 0 from the right, the values of our function f of x seem to be closing in on 1. However, since there was no single number, L, there is no one number that the values of our function f of x are approaching as x approaches 0 from both directions, we would say that the limit that we were interested in, that is the limit as x approaches 0 of f of x, does not exist. So this example illustrates that we could consider one-sided limits, what's happening to the values of a function as we approach a number from one direction. And we see that if we were to have two different limiting values for a left-hand and a right-hand limit, that the limit of the function itself would not exist. There's no single number which we're approaching. So let's make these definitions of one-sided limits a little more formal. So here we'll say, let f be some function, and let a and L be some real numbers. So we say the left-hand limit of a function f of x as x approaches a is equal to L if the values of our function f of x can be made arbitrarily close to L, that is, as close as we want to the number L, by taking values of x sufficiently close and less than the number a. So here, that extra condition where we're taking values of x less than a is used to distinguish a left-hand limit. And the notation that we're using is the limit as x approaches a, where the little minus sign beside the a is used to denote a left-hand limit of the function f of x is equal to L. Now, in a similar way, we can define a right-hand limit of f of x as x approaches a as being equal to the number L if the values of the function f of x can be made arbitrarily close to the number L by choosing values of x sufficiently close and greater than the number a. So this is denoted as the limit as x approaches a from the right, so the little plus denotes a right-hand limit of f of x is equal to L. And in the case that we're talking about a limit of a function as we approach a number from both the right and left-hand sides, we would use the same notation for a limit that we saw in section 11.1. And to distinguish that limit, we would sometimes call this the two-sided limit of our function. So from the example that we had considered at the beginning of this section, or a couple of the examples we saw at the end of section 11.1, we arrive at the following theorem, which is called the one-sided limit theorem, which says if we have a function f and real numbers a and L, the limit of f of x as x approaches a would be equal to L if and only if the left-hand limit of that function as x approaches a is equal to the right-hand limit of the function as x approaches a, and both of those limiting values are equal to L. So what that means is that the function f has a two-sided limit at x equals to a exactly when it has both a left-hand limit and a right-hand limit at a, and those limits are equal. So conversely, if the left and right-hand limits of a function as x approaches a are not equal to each other, that means that the two-sided limit does not exist, as we've seen in the first example of this section and at the end of the last section. So let's look at some examples working with one-sided limits. So here we are given the graph of a function f below, shown here in red, and we're asked to find the following limiting values if they exist. So let's start with this first one. We're looking for the limit of f of x as x approaches -2 from the left. So on our x-axis here, the horizontal axis, we're closing in on -2 from this left-hand side. And if we follow the corresponding values of our function, f of x, as we're closing in on -2, we can see that our y values seem to be approaching -1. So this left-hand limit of our function as x approaches -2, we would say is equal to -1. Now in the next part, we're asked for the limit of f of x as x approaches -2 from the right-hand side. So here, we're closing in on -2 from the right, and we can see from the graph of our function, if we follow along with the corresponding y values, they're also approaching this value of -1. So we've shown that both the left and right-hand limit of this function as x approaches -2 are equal to -1. Therefore, in the next part of this problem, we're asking for the two-sided limit of f of x as x approaches -2. And the one-sided limit theorem says, well, if the left and right-hand limits of f as we approach -2 are equal, then the two-sided limit must equal that same value, -1. Now, in the next part of this problem, we're asked for the value f of -2. So if x is actually equal to -2, we want the corresponding value of our function. And looking at the graph we're given, well, we see that there was a hole in the graph of f of x, and there is a closed point when x is equal to -2, which corresponds to the point -2, -3. So the value of our function when x is equal to -2 is -3. So we see from this first example that the limit of a function might be different from the value of the function at a particular x value. So let's look at some other ones. In this same example, we're asked for the left-hand limit of f of x as x approaches 3. So here, as our x values are closing in on 3 from the left-hand side, if we look at what's happening to the corresponding values of our function by looking at the graph of our function, we see they seem to be closing in on 2. So our left-hand limit of f of x as x is approaching 3 would be 2. And then we're asked for the right-hand limit of f of x as x approaches 3. So as we're closing in on 3 from the right-hand side, if we trace out the corresponding values of our function, by looking at the graph, we see that they seem to be approaching the value -2. So this right-hand limit would be -2. And then in the next part, we're asked for the two-sided limit of f of x as x approaches 3. Now, in this case, we've shown that the left-hand and the right-hand limits were two different numbers, +2 and -2. Therefore, by the one-sided limit theorem, if those left and right-hand limits are not equal, this two-sided limit does not exist. Since there is no single number that we're approaching from both directions, the two-sided limit is undefined or does not exist. And then in the last part of this example, we're asked for the value f of 3. So when x is actually equal to 3, we can see from our graph here, well, there was a hole here and a hole here, but there is a closed point here at the point 3, 1. So when x is equal to 3, the value of our function is 1. So a function which is defined at a certain x value, say x equals 3, may not have a limit at that same x value if we have different left and right hand limits. Okay. So let's consider a similar problem. Here we are given a function f, which is piecewise, and it's defined in the following way. And in part A, we're asked to sketch the graph of that function, f of x. So let's see if we can sketch this graph in pieces. So here, let's maybe sketch it out from left to right. So we're told that the graph is, or the function is 2 minus x if x is less than -1. And that's a strict inequality here. So let's think about when the value of x is equal to -1, the value 2 minus x would be close to 3. So from -1, 3, well, we're going to have an open point there. An open point because that was a strict inequality. X has to be strictly less than 1. So to the left of x equals -1, our graph is the graph of 2 minus x, which is a line with slope -1. So here, if I were to want to see what my graph looks like, we could choose another x value, say -2, and we find that the value of the function would be +4. If we chose x as -3, the value of our function would be +5. So we have the line, or line segment, which is shown here. And again, we have this open point at x equals -1, since that inequality was strict. So let's see what our definition changes to. As soon as x is equal to -1, our function is defined as x itself. So if x is equal to -1, the value of our function would also be -1, and we have a closed point there. Since our inequality was x is greater than or equal to -1. And we're moving up through x equals 1. And the graph of our function, y equals x, would be the line of slope 1, whose y-intercept is 0. So as we approach x equals 1, the values of our function are approaching 1. And we have an open point when x is equal to 1, since this inequality was strict here. Now moving to the next part of our domain, we see if x is equal to 1, our y value is defined as 4. So when x is 1, we have a y value of 2, 3, 4. So we have a closed point at 1, 4. And then as soon as x is greater than 1, the definition of our function changes to 4 minus x. So if we're very close to 1, the values of the function on this last part of our domain would be close to 3. So we're going to have an open point at 1, 3. And from here, the graph of our function is linear with a slope of -1. So if we were to choose, for instance, x equals 2, we would have a y value of 2. If we choose x equals to 3, our y value is 1. So we have a line of slope -1 for all values of x greater than 1. So our graph looks something like the following. Now, in part B, we are asked to find the values of x for which our limit does not exist. So we know our limit will not exist if the left and right hand limits are different numbers. So anywhere that the graph of our function makes a jump in its definition, then we have a limit which does not exist. So the first value of x, if we're reading from left to right, would be at x equals -1. We see there was a change in definition of our function, or a jump in the values of the function at x equals -1. So here, at x equals -1, the limit does not exist. We can verify that because if we consider the left-hand limit as x approaches -1, we see as we're closing in on 1 from -1 from the left, our y values are closing in on 3. And the right-hand limit of the function as x is approaching -1, we can see is closing in on -1. So since we do not have a left and right hand limit which agree, the limit itself, or the two-sided limit, does not exist. Now another point where we have a value or a limit which does not exist would be at x equals +1. Here we see from the graph that we've sketched in part A, the left-hand limit of f of x as x approaches +1 is 1, and the right-hand limit as x approaches 1 of f of x, we see from the graph of our function, is 3. So here we have determined from our graph these values of x where our limit does not exist. Now in the next part of this section, we're going to discuss infinite limits, which we had looked at informally at the end of our section 11.1 material. So let's consider the following problem. We are asked to find the limit as x approaches 0 of 1 over x squared if it exists. So there's a couple of ways that we could go about finding this. So one way would be to consider a table of values. Let's say for x and 1 over x squared. Now we know when x is equal to 0, this function is undefined because we cannot have division by 0. So let's consider values of x which are close to 0 but not equal to 0. So maybe I'll take a value which is to the right of 0 but close to 0, maybe 1/10. Now let's see what our corresponding y value would be, or the value of our function. So we have 1 over x squared, that is 1 divided by 1/10 squared. Now recall when we divide by fractions, that's the same as multiplying by the reciprocal of our denominator. So 1 over 1/10 squared would be the same as 10 squared, or 100. If we move a little bit closer to 0 from the right-hand side, let's say we take 1 over 100, well, our value of the function would be 1 over 100 squared, which is the same as 100 squared, or 10,000. Now, if we were to take an x value which is to the left of 0, but close to 0, let's say -1/10, well, we would have the same value as when we plugged in +1/10, since our denominator is x squared. It doesn't matter if we plug in a positive or a negative value for x. When we square it, we're going to get the same expression. So here we would have 100, the same value we had for +1/10. Or if we take -1/100th, move a little bit closer to 0 from the left, we would have the same value that we had for +1 over 100, which was 10,000. So we see as the values of x are closing in on 0, from the left or right hand sides, the values of our function f of x are getting larger and larger and positive. So we would say in this case that the limit as x approaches 0 of 1 over x squared is positive infinity. The values of the function 1 over x squared are becoming unboundedly large in the positive direction as we get closer to 0. Now we could also see that by examining the graph of this function. So if you consider the graph of 1 over x squared for values of x that are close to 0, you have something that looks like this. So we see as our x values are closing in on 0 from the left or right-hand side, our functional values are increasing without bound in the positive direction. So in this case, we say that we have an infinite limit or a positive infinite limit. So here, let's define this infinite limit a little more formally. Let's say that we have a function f and a as some real number. So if the values of f of x can be made arbitrarily large, that is, as large as we want, by taking x sufficiently close but not equal to some number a, then the limit of f of x as x approaches a, we say approaches infinity, and this is denoted as the limit as x approaches a of f of x equals infinity. Now we could define similarly a limit if the values of f of x can be made arbitrarily large but negative by taking x sufficiently close but not equal to a. We say the limit of f of x as x approaches a approaches negative infinity. And we have a similar notation. Now, associated with infinite limits, we can define asymptotes of the graph of a function. So let's look at the definition of a vertical asymptote. So we would say the vertical line, x equals a, is called a vertical asymptote of the graph of a function, y equals f of x, if either the left-hand limit of f of x as x approaches a is positive or negative infinity, or the right-hand limit of f of x as x approaches a is positive or negative infinity. So as some examples to illustrate vertical asymptotes, I've given the graphs of a couple of functions below. And we can see from our first graph in this left-hand plot, it looks like the line x equals 2 is a vertical asymptote, since the left-hand limit of my function as x approaches 2 is negative infinity, and the right-hand limit of my function as x approaches 2 is positive infinity. Now in the function plotted in the right-hand figure, by examining this graph, it looks like the lines positive and negative 1 are vertical asymptotes for this function. We see the left-hand limit as x approaches negative 1 is positive infinity. The right-hand limit as x approaches negative 1 is negative infinity. The left-hand limit as x approaches positive 1 is negative infinity. And the right-hand limit as x approaches positive 1 is positive infinity. So if any of those one-sided limits are infinite, that's when we would say that our function has a vertical asymptote at that line. So given that, let's consider the following. We're asked to find the given limits if they exist. So here we're looking at the limit as x approaches 3 from the left of 1 over x minus 3. So here there's a couple of ways that we could go about finding this limit. We could consider the graph of the function, 1 over x minus 3, which we'll be able to use for each part of this problem. So to the side, let's do a little scratch work where we'll illustrate the graph of 1 over x minus 3, which is similar to the graph of 1 over x, but it's shifted to the right 3 units. So we have, for x equals 3, a graph that looks like the following. So this is a graph that's very similar to the graph of 1 over x, but it has been shifted 3 units to the right. So as x is approaching 3 from the left-hand side, we can see the values of our function are approaching negative infinity. Therefore, we have a negative infinite limit here. Now, if we weren't sure what the graph looks like, we could also consider this by looking at a table of values. So let's say that we have x and 1 over x minus 3. So we want to take values of x which are approaching 3 from the left. So maybe we could take 2.9. So I would have 1 divided by negative 1/10, which would give me negative 10. If I move a little closer to 3 from the left, let's say 2.99, I would have 1 divided by negative 100th, which gives me negative 100. Or if I take 2.999, I would have for my function 1 over negative 1,000, a 1,000th, which would give me negative 1,000. So we can see the closer that we're getting to 3 from the left, the values of our function are getting larger, but in the negative direction. Now in part B, we have the same sort of problem for 1 over x minus 3, but we're approaching x from the right-hand side. So examining our graph, as we approach 3 from the right, we can see the values of our function are increasing without bound in the positive direction. So our limit would be a positive infinite limit. Now again, if we weren't able to sketch that graph, we could determine this limit by considering a table of values for x and 1 over x minus 3. So if we take a value of x that is slightly greater than 3, let's say 3.1, we would have 1 over 1/10, which is positive 10. If we take 3.01, we would have 1 divided by 1/100th, which would be 100. And if we take 3.001, we have 1 divided by 1,000th, which would be 1,000. So as our values of x are getting closer to 3, we can see the values of our function are getting larger in the positive direction. And so in part C, we are asked what is the two-sided limit of 1 over x minus 3 as x approaches 3. And from parts A and B, we saw we had different left and right-hand limits. So using the one-sided limit theorem, we could say that this two-sided limit that we're asked for does not exist. There is no single number, which we are approaching from both the left and right-hand sides as we're approaching 3. Okay. So let's look at some other problems involving infinite limits. So here we are asked to find the given limits if they exist. So in part A, we have the right-hand limit as x approaches 0 of x minus 1 over x squared divided by x plus 2. Now typically the first thing that we always try for limit problems is to plug in the given value of x. So if we try that here, plugging in x equals 0, we have negative 1 divided by 0. So we're going to typically see an infinite limit when we have a fraction of this form, a non-zero number divided by 0. Because here we know that our denominator is being made smaller and smaller the closer that x becomes to 0. So if I'm dividing by smaller and smaller numbers, my ratio will become larger and larger. That is, approaching either positive or negative infinity. Now the question becomes, well, which one? Do we have a positive or a negative infinite limit? And in order to address that question, let's consider what side we are approaching from. So in this example, we are taking a right-hand limit as x approaches 0, which means all of the values of x are close to 0, but positive. So let's consider the sign of our function. So looking at the numerator, if we have values of x which are positive, but very small, close to 0, then x minus 1 will be negative. And our denominator is x squared, which is always positive, times x plus 2. So if x is equal to, or if x is approaching 0 from the right, that is, if x is positive, x plus 2 will also be positive. So our ratio is the ratio of a negative number divided by a positive number, which must be negative. Therefore, we would say that this limit is an infinite limit in the negative direction. Now in part B, we have the same sort of question. The left-hand limit as x approaches 0 of the same function. So again, if we just try plugging in 0, we have negative 1 divided by 0, which makes us suspect that we have an infinite limit, since our denominator is becoming smaller and smaller. Now the question is whether it's a positive or negative infinite limit. So again, let's consider this question about the sign. So if we're taking x approaching 0 from the left, that is, if x is close to 0 but negative, then our numerator, x minus 1, well, if you have a negative number and you're subtracting 1, it's still negative, divided by x squared, which is always positive, times x plus 2. Now if x is negative but close to 0, and we're adding 2 to that value, then we get a positive number. The 2 that we're adding is greater than whatever small negative number we're taking for x. So we would have a negative divided by a positive again, which means that our limit would be a negative infinite limit. So then in part C, we're asking for the two-sided limit of that function as x approaches 0. And in parts A and B, we saw that both the left and right-hand limits were negative infinity. Therefore, our two-sided limit would also be a negative infinite limit. Okay. Now, in the last part of this section, we're going to talk about limits at infinity. So the first type of infinite limits that we were talking about were if the values of our function are becoming unboundedly large as x is approaching some number from the left or right-hand side. Now, another problem of interest in many applications is what happens to the value of a function as x approaches, say, positive or negative infinity. And where we might see this come into play is if we want to know what is happening with the value of a function over a long period of time. That is, as time becomes infinitely large, what's happening with the quantity. So these types of limits are referred to as limits at infinity. And let's introduce a definition. So we would say if we have a function f and some real number L, if we can make the values of our function f of x arbitrarily close to L by taking values of x sufficiently large, then we say the limit of f of x as x approaches positive infinity is equal to L. And this is denoted as follows. We would say the limit as x is approaching positive infinity of f of x is equal to the number L. Now similarly, we could define a limit at negative infinity. So if we can make the values of a function f of x arbitrarily close to a number L by taking values of x sufficiently large but in the negative direction, then we would say the limit of f of x as x approaches negative infinity is equal to L, and that's denoted as follows. The limit as x approaches negative infinity of f of x is L. Now for these limits at infinity, we can use these to define horizontal asymptotes of a function. So we would say that a line y equals L, that is a horizontal line, is a horizontal asymptote of the graph of a function if either the positive infinite limit of f of x is equal to L, or the negative infinite limit of f of x is equal to L. So in the figures that I've shown here, I've illustrated some examples of horizontal asymptotes. So in our left-hand figure, we can see that our function first has a vertical asymptote at, it looks like x equals 2, since our right-hand limit as we approach 2 is infinity, and our left-hand limit as x approaches 2 is negative infinity. And we also have a horizontal asymptote. It looks like at y equals 2, because as x becomes infinitely large, we see the values of our function seem to be closing in on that horizontal line, or as x becomes infinitely large in the negative direction, the values of our function seem to be approaching that line. Now in this right-hand figure, we have the graph of a function which seems to be oscillating, and as x is becoming infinitely large, the values of our function seem to be decreasing, approaching a horizontal line, which is the x-axis, or the line y equals 0. And similarly, as x approaches negative infinity, we see the values of our function seem to be closing in on that same horizontal line. So these would be examples of horizontal asymptotes for our function. So as an example to consider limits at infinity, let's look at the following. In part A, we are asked to evaluate the limit as x approaches infinity of 1 over x. Now there's a couple of ways we could do this. One way would be to look at the graph of the function 1 over x. Another approach would be to consider a table of values. So let's start by looking at a table of values for x and 1 over x. And we're looking for a limit as x is approaching positive infinity. So let's start by taking maybe just a small value of x, say x is 1, in which case 1 over x would be 1. And if we start taking x to be larger, let's say we take x as 10, then 1 over x would be 1/10. If we make x larger, let's say 100, then our function would be 1/100th. If x is taken as 1,000, the value of our function is 1 over 1,000. So we can see here that as the values of x are becoming infinitely large, the values of our function are 1, 1/10, 1/100th, 1 1,000th. They seem to be getting smaller and smaller, approaching 0. So we would say that the limit of 1 over x as x approaches infinity is 0. Now we could also see that from the graph of this function. So if we think about the graph of the function 1 over x, we have something that looks like the following. And we can see here that as x is becoming infinitely large, the values of our function are decreasing towards 0. Similarly, we didn't ask it in part A, but if we were to consider the limit as x approaches negative infinity of 1 over x, we would also have a 0 limit. The values of our function are becoming smaller and smaller. All right. Now in part B, we're asked for a similar limit, the limit as x approaches negative infinity of 2 over x cubed, which we could find by using a table of values or the graph. So for this one, again, let's consider a table of values, say x and 2 over x cubed. And we're taking values of x approaching negative infinity. So let's start by taking a small negative number, say -1. So the value of our function in that case is -2. If we take x to be a little larger, let's say -10, the value of our function becomes -2 divided by 10 cubed, which is 1,000. If we go a little larger, let's say -100, the value of our function is -2 divided by 100 cubed, which would be the following, -2 over 1 million. So we can see as the values of x are getting larger and larger in the negative direction, the values of our function are getting smaller and smaller, from -2 to -2 over 1,000 to -2 over 1 million. So they're starting to close in on 0. So we would have a limiting value of 0 here. Now in this example, the point that we want to make is in general the following. If we have an infinite limit where we have a fixed constant, let's say 1, or in part B, the number 2, and we're dividing by some power of x, well, as x gets larger in the positive or negative direction, that means that this ratio is getting smaller and smaller. We're taking a fixed value, like 1 or 2, and we're dividing it among larger and larger numbers. Therefore, that ratio is tending towards 0. So we're going to make use of that fact in our next few examples. So in these next examples, we are considering infinite limits of rational functions. Those are quotients of two polynomials. And we're asked to find these limits if they exist. Now there's a general technique for finding infinite limits of rational functions, and the idea is the following. So when we look at our rational function, we're going to identify the largest power of x that appears in the denominator. So when we look at our function in part A, the largest power of x, which appears in the denominator, is this x cubed term. We've got 2x cubed. Now the way that we're going to evaluate these limits is by multiplying the numerator and denominator of this rational function by the ratio 1 divided by that highest power of x that appeared, in this case x cubed. Or equivalently, we can think of we're dividing the numerator and denominator by x cubed, whatever the highest power of x is that appears in our denominator. Now let's see what that buys us. We have the limit as x approaches infinity of, well, let's look in our numerator. We had a 7x cubed, and then we're dividing by x cubed. So that leaves us with just a 7. And then plus we had a 4x divided by x cubed, which reduces to 4 over x squared. Then we're dividing by, in our denominator, we had 2x cubed divided by x cubed, which leaves us with 2. Then minus x squared over x cubed reduces to 1 over x, and then plus 3 divided by x cubed. Now using the properties of limits, we know that the limit of a quotient is the quotient of the limits. So I can think about this as the limit of the numerator, which was 7 plus 4 over x squared, divided by the limit of the denominator, which was 2 minus 1 over x plus 3 over x cubed. And again, using properties of limits, well, the limit of a sum in the numerator is the same as the sum of the limits. So I can take the limit of each piece here. So let's see what we have for our numerator. We have the limit of a constant, 7, which using the constant property must equal 7. And then plus the limit as x approaches infinity of 4 over x squared. So we just said in the previous example, if we have a fixed constant, like say 4, and we're dividing by larger and larger numbers, that ratio is getting smaller. It's approaching 0. So for our numerator, we're going to have 7 plus 0. And then we are dividing by, if we take the limit of each term in our denominator, we have the limit of a constant 2, which is 2, minus the limit of 1 over x as x approaches infinity, which we said in the last example is 0, plus the limit as x approaches infinity of 3 over x cubed. So again, if we have a fixed constant 3 and we're dividing by larger and larger values, that ratio is approaching 0. So altogether, we're left with 7 over 2 for our limit. Now, one thing to notice, or one thing that I'll point out in this example, is in the case that our numerator and denominator in this rational function both have the same highest power of x. In this case, the highest power of x on both top and bottom is x cubed. We see that our limit ended up being 7/2, which was the ratio of the lead coefficients for those highest powers of x in top and bottom, 7 over 2. And in general, that will always hold in the case that we have an infinite limit of a rational function with the same highest power on top and bottom. We can just look at the ratio of those lead coefficients to get our answer immediately. So in part B, we've got a similar problem. The limit as x approaches negative infinity of this rational function. So my method is the same here. I'm going to look for the highest power of x on top and bottom. So I see for my numerator, it is x to the fourth. For the denominator, it is x to the fifth. So they don't have the same highest power, so I can't use the same method that we did in part A. But where I just look at the ratio of the lead coefficients for those highest powers. But in general, I can make use of the same idea that we used in part A, where I'm going to find the highest power of x that appears in the denominator, which we've mentioned is x to the fifth, and I'm going to divide the numerator and denominator by that highest power of x. Or equivalently, divide top and bottom by x to the fifth. So we have the limit as x approaches negative infinity of, for our numerator, we have x to the fourth over x to the fifth, which is 1 over x, minus x squared divided by x to the fifth would be 1 over x cubed, plus 1 divided by x to the fifth. And then all over our denominator, which was x to the fifth divided by x to the fifth, which leaves us 1, plus x cubed over x to the fifth is 1 over x squared, and then minus x divided by x to the fifth is 1 over x to the fourth. So again, making use of the limit properties, I can take the limit of the numerator and denominator separately. So looking at the limit of our numerator, well, as x becomes larger in the negative direction, 1 over x cubed, and 1 over x to the fifth are all approaching 0 because we have a fixed number and we're dividing by larger values of x. So we would have 0 minus 0 plus 0 divided by, taking the limit through our denominator, we have the limit of a constant 1, which is 1, plus the limit of 1 over x squared or 1 over x to the fourth as x gets large are both 0. So we would have plus 0 minus 0, which leaves me with 0 divided by 1, which is 0. So in this example, we can point out kind of a general concept. In the case that we're looking at an infinite limit of a rational function, that is quotient of two polynomials, if the highest power in the denominator is greater than the highest power in the numerator, then this ratio will be getting smaller and smaller. That is, our denominator is growing more rapidly than the numerator, so the ratio is becoming smaller, tending to 0. So in general, when we're taking an infinite limit of a rational function, if the highest power of x is in the denominator, then immediately we know that we'll have a 0 value for our limit. We no longer have to go through these steps to justify it. So in our last example, part C, we have an infinite limit of a rational function. So again, let's see where the highest powers are in the numerator and denominator. Here we have a highest power of x to the fourth in the numerator, x cubed in the denominator. So it doesn't fall into the categories that we saw in parts A or part B, but we can use the same general approach that we did in parts A and B, where we identify the highest power of x in our denominator, which was x cubed, and we're going to divide the numerator and denominator by that highest power which appeared, which we just said was x cubed. So we have the limit as x approaches infinity of when we divide our numerator by x cubed, we're left with x plus 2 over x squared plus 3 over x cubed, all over, when we divide our denominator by x cubed, we have 1 minus 1 over x squared. So now, taking the limit of the numerator and denominator separately, well, for our numerator, this first term, x, as x approaches infinity, is becoming infinitely large. And the second two terms, 2 over x squared or 3 over x cubed, are both approaching 0 as x gets large. Now, taking the limit through our denominator, we have the limit of a constant, 1, which is equal to the same constant, minus the limit of 1 over x squared as x becomes large is 0. So we have something of the form infinity divided by 1. So if you take an infinitely large positive number and you divide it by 1, the limit is still infinitely large. So here, in this third part of our example, part C, we can generalize this as we did in parts A and B and say, in the case that we have an infinite limit of a rational function and the highest power of x is in the numerator, that means that the numerator will grow more rapidly than the denominator. So the ratio is becoming unboundedly large. We'll have an infinite limit, which is either positive or negative. And to determine whether it's positive or negative, we have to look at what the sign of the numerator and denominator are doing. Let's consider another example where we will identify vertical or horizontal asymptotes of a function directly from our graph. So in part A, we're told to use this graph to identify vertical or horizontal asymptotes. And here we have the same graph that we were looking at earlier. For this function, we see that there appears to be a vertical asymptote passing through the point x equals 2 and a horizontal asymptote passing through y equals 2. So for this function, we would say our horizontal asymptote would be the line y equals 2, and the vertical asymptote is the line x equals 2. So in part B, we have the graph of a similar function. And by examining our graph, we see that we have infinite limits as x is approaching -1 or as x is approaching +1. So these would be vertical asymptotes. At x equals -1 or x equals 1. And we can see from our graph that it appears that we have a horizontal asymptote passing through y equals 1. Okay, so if we have the graph of a function provided, it's not difficult to recognize vertical or horizontal asymptotes. So in our last example for this section, we're given a function, which is a rational function, a quotient of two polynomials. And we are asked to determine the vertical and horizontal asymptotes of each of these functions. So in order to determine vertical asymptotes, we're trying to find where we have a positive or negative infinite limit. And we said in order to have a positive or infinite limit, an infinite limit, we would have to have a function which has a limit of the form some constant divided by 0. So if we have a fixed number and we are dividing by smaller values, that is, our denominator is approaching 0, we know that the ratio is becoming infinitely large. So to determine the candidates for a vertical asymptote, we will set our denominator, which was x plus 5, equal to 0. So we see here that x is equal to negative 5. And if we consider a limit as x approaches negative 5, say from the left, or a limit as x approaches negative 5 from the right of this function, 3x minus 1 over x plus 5, let's see what we get. So we suspect these limits will be infinite. And let's see if we can determine our sign. So here, if we are considering x approaching negative 5, it looks like our numerator is approaching negative 16, and the denominator is approaching 0. So that ratio is becoming unboundedly large. And to get the sign of the infinite limit, let's consider the sign of our numerator and denominator. So if we're approaching negative 5 from the left, our numerator is approaching negative 16. So the numerator will be negative, and our denominator, x plus 5, well, if we're taking values of x that are less than negative 5, for instance, negative 6, we see the denominator would also be negative. So the ratio of those two negative numbers would be a positive value, so we have a positive infinite limit. And as x approaches negative 5 from the right, well, our numerator is still approaching negative 16, so its value is negative. However, if we're approaching negative 5 from the right, that is taking values of x that are greater than negative 5, for instance, negative 4, we see that x plus 5 would be positive. So the ratio of a negative over a positive would give us a negative infinite limit. So here we have a vertical asymptote of x equals negative 5. And to consider horizontal asymptotes, we look at the limit of our function as x approaches positive or negative infinity. So here, the limit as x approaches positive or negative infinity of 3x minus 1 over x plus 5. Well, let's recall what we had seen in our previous example. If we have the infinite limit of a rational function, we would ask ourselves where the highest power of x lies. And in this example, both the numerator and denominator have the same highest power of x, namely x to the first. So our limit should be given by the ratio of the coefficients for those highest powers. In this case, 3 divided by 1. So we had 3x over 1x. So I claim this limiting value is 3. You can see that more formally if you divide top and bottom through by x and take the limit piece by piece using the limit loss. So according to the definition of a horizontal asymptote, if our positive or negative infinite limit is approaching some fixed value, in this case 3, that means that that horizontal line is a horizontal asymptote. All right. Now you can verify this if you make use of a graphing calculator or a graphing tool online. You can sketch the graph of this function and verify that it does have those vertical and horizontal asymptotes. So for our last part, part B, we have f of x is the following function. And again, we want our vertical and horizontal asymptotes. So to consider vertical asymptotes, again, we would take our denominator, x squared minus 2x minus 3, and set it equal to 0. Now this quadratic can be factored as x plus 1 times x minus 3, which is 0. So our candidates would be x is -1 or +3. Now, a word of warning here, just because the denominator is 0 does not mean that you have a vertical asymptote at this point. We need to make sure that we have a positive or negative infinite limit. So let's consider what happens as we're approaching, say, -1. So here, we have the limit as x is approaching -1 of the following function. So if we try to evaluate this limit by plugging in -1 for x, our numerator is 5 minus 5, or 0, and our denominator is 0. So we would have something of the indeterminate form 0 over 0. And as we saw in the last section, to evaluate this type of limit, we could consider factoring the numerator and denominator. So here our numerator factors as x plus 1 times x plus 4. And the denominator, we've already said, factors as x plus 1 times x minus 3. So we can cancel the common factor of x plus 1 on top and bottom. And we have the limit as x approaches -1 of x plus 4 over x minus 3, which leaves us with 3 divided by -4, so -3/4. And recall the definition of a vertical asymptote is that this limit had to be infinite. So since this limit is not infinite, that means that x equals -1 is not a vertical asymptote. If you look at the graph of this function, there's a hole at -1. It's undefined when x equals -1 since we have division by 0, but it does not have an infinite limit there. So let's consider the value x equals 3. So if we consider a limit as x approaches 3 of our function, we have, if we're plugging in the value of 3, a numerator, which is approaching 9 plus 15 plus 4, and a denominator, which is approaching 0. So we do suspect that we would have a positive or negative infinite limit, depending on whether we're approaching 3 from the left or the right-hand side. So here, if we think about this in a little further detail, we can factor our numerator as x plus 1, x plus 4, over x plus 1 times x minus 3, and again cancel that common factor of x plus 1 on top and bottom. So we have the limit as x is approaching 3 of x plus 4 over x minus 3. So here, depending on what side of 3 we're approaching from, we will have a positive or negative infinite limit. If we approach 3 from the left, we have a negative infinite limit. If we approach 3 from the right, we have a positive infinite limit. Since we have infinite limits at x equals 3, that means that x equals 3 is our only vertical asymptote. And to determine horizontal asymptotes, we would need to consider the limit of our function as x approaches positive or negative infinity. So in this example, we see we have an infinite limit of a rational function, and the highest power of the numerator is same as the highest power in our denominator. Therefore, by our earlier discussion, the limiting value would be the ratio of the coefficients for those highest powers. So that is 1x squared divided by 1x squared, which is 1. So here we have a horizontal asymptote of y equals 1. So in this section, we've discussed the idea of one-sided limits and seen that if the left and right hand limits are not equal, then the two-sided limit does not exist. And we've considered examples of limits involving infinity to define either a vertical or a horizontal asymptote for the graph of a function. And we had come up with a technique for evaluating the infinite limit of a rational function by identifying where the highest power of x appears. If it's the same highest power on top and bottom, your limit is the ratio of those coefficients for the highest powers. If the highest power is in the denominator, your infinite limit approaches 0. And if the highest power is in the numerator, you have a positive or infinite a positive or negative infinite limit depending on what the sign of your numerator and